rectangular or Cartesian coordinates. So rectangular or Cartesian, or sometimes called complex, coordinates are in a system where points are identified on a rectangular grid. So that point is identified as 2, 3 because it is right 2 and up 3. If I had actual graph paper up here, the graph paper is set up with little tiny rectangles. Now you'll say, oh, they're squares. Squares are rectangles. This is called a rectangular system. This is what you've always dealt with. Points are identified in terms of a horizontal and a vertical. The graph paper you use has little boxes on it, little rectangles on it. Well, what we're going to do today is change the framework so that we are looking at points from a different standpoint. Now we're going to be looking at points on a circular system, which is referred to as the polar system. So points are identified, this is the paper that I gave you. Points are identified, let's say this point right here, not in terms of over so many and up so many, but in terms of how far out are you from this point, which is called the pole. How far out are you? Well, how far out am I? 1, 2, 3, 4. I'm 4 units out. At what angle? Because there's lots of points that are 4 units out, right? But I want the particular one that is at an angle of 30 degrees. So this point right here would be identified in polar coordinates as the point 4, 30. Okay? So what about this point right here? What would he be identified as? This is the axis right here. That would be 5, 75. That point right there is 5, 75. Polar coordinates are not an X and a Y. Polar coordinates are an R and a theta. Now the R, I always think of as radius, but it actually is Greek on a row. Doesn't have anything to do with radius, but it sure does in my mind have to do with radius. And theta is the angle in standard position. Michael?
Can R ever go past 5?
Oh yeah, just like if you're graphing on a regular thing, you just have to change your scale. So instead of these being 1, 2, 3, 4, 5, you could make them 10, 20, 30, 40, 50, or 0.1, 0.2, 0.3. So yes, you can change your scale. Now, the angles aren't going to change because no matter what, you got 0 to 360 and that's all you've got. But yes, you can change the scale on your units, or on your radii. Now, one huge difference between rectangular and polar coordinates is that if I asked 1 million people who are, reasonably intelligent to give me the coordinates of this point, all 1 million of them would say 2, 3. There is no other way to name that point. But in polar coordinates, there's a lot of ways to name this angle, or to name this point right here. Now, most of us are going to say 4, 30. But what else could I say besides 4, 30? What would be another way to get me to that very same point? 4 what?
4, Or 120.
No, 120 would put me over here.
Or 390.
390 would. If I said, let's graph for 390,
Would it be negative 390?
that would mean, no, 390. What does 390 do? 390 goes all the way around and 30 more. Wouldn't that put me in the same spot? Now, if you wanted to go negative, it would be for negative 330. That would put me in the same spot too, right? There are lots of angles you could name that would put you at that spot. Is everybody in agreement? What do we call all those angles? We call them coterminal. That's right. All the coterminal angles are going to put you in that very same spot. And how do we find coterminal angles? We either add 360 or subtract, right? So we've got a couple of them up there, but there are zillions more. All right, it gets worse than that. Because not only can you finagle the angle, but you can mess around with the radius. Wait a minute, you're saying, wait a minute. If we have to be 4 units out, 4 units is 4 units. Well, guess what? You can actually have R be negative. Now, what does it mean when you see a negative R? Well, I'll tell you, this point right here would be exactly the same as all of these. Okay? Now, here's the deal. When your radius is negative, what that means is the point gets plotted on the opposite side of the circle. So this says I'm at 210 degrees, which is right here. But the negative tells me that I get plotted on the opposite side of the circle. Well, what's the opposite side of a circle? How many degrees to get to the opposite side of the circle? 180. So this negative tells me I don't plot at 210. I plot 180 degrees away from 210. So what's 180 degrees away from 210? 30, if I go positive, right? So where would you plot negative 3, 240? Where would you plot negative 3, 240? Well, it's going to be on the circle with a radius of 3, but it's going to be 180 degrees away from 240. That negative tells you you're on the opposite side. So what would that be? 60. So this point would get plotted here. Anytime you have a negative radius, the point is going to be plotted 180 degrees different. Okay? We're kind of early in the game for you to really be thinking about this, but we're going to be graphing things and plotting points, and you're going to get negative R's, and you're going to have to be able to deal with them. Okay? So now we know how to deal with them. What if, could you figure out where to plot negative 2, negative 105? Could you figure out where to plot that point? Well, first of all, you can't plot a negative R, so you know you're going to have a radius of 2, but it's going to be plotted 180 degrees away from this, so that would be at 2, 75. That's where you would plot that point. Okay? Some of the problems in the homework, now the paper I gave you, I've labeled it all in degrees. They're labeled in degrees, right? Look at it, labeled in degrees. Some of the problems in the homework are in radians. They ask you to plot points in radians, so they might say plot 2, pi over 2. Plot that point. Well, we know how to change radians into degrees, right? So where's this going to be plotted?
290.
290. So it will be plotted right here. So if they're in radians and that's confusing you, change them to degrees, and you should be fine. Okay? Now, that's kind of the ground level. Now we're going to see if we can change from one system to the other. So in other words, we're going to see if we can change, let's say 3, -4 into polar coordinates.
So it's 3, -4, like a regular Cartesian.
That's Cartesian. If we're changing into polar, then we are starting with X and Y. So you know what I'm going to do. It's what I do on every problem I do. I draw a picture of it. So I'm going to plot the point over 3, down 4. My little butterfly bow tie that goes with me everywhere.
So that's going to be the hypotenuse going to be 5.
Now envision this, right? Isn't this R? So it's going to be 5, right? Now I need to know, I know I'm 5 units out. I know my radius is going to be 5.
Now you got to find that angle.
I got to find the angle in standard position. So I'm going to use second tangent. Find that angle. Second tangent. So I got this angle to be 53.13. Now you need to read the directions, because sometimes the directions are very specific. We just talked about the fact that there are lots of ways you can name that angle. Sometimes the directions say that theta, your angle, has to be between 0 and 360. So if that's what it says, then you can't say -53. Now, would -53 be an okay response to get me to this point? Yeah. But if the directions say you're between 0 and 360, which they very often do,
So then you use that.
then this is going to be the angle you're going to use, right? Which is 306.87. And there's the answer to the question. There are your polar coordinates. Now, before you say anything, I want to remind you that you have done that exact thing over and over again in the last few sections. Because what we just did was find the magnitude of a vector and its direction angle. That's all. R and theta are the magnitude of the vector and the direction angle. Nothing tricky or different or new about that. All right, let's try one more. And then we'll go the other way. All right, so now we're going to change, let's say -1, -4 into polar coordinates. All right, so here we go. We're changing -1, -4. So we know x is -1, y is -4. What's my radius? Square root of 17. You are finding r and theta. R is the magnitude of the vector. Think of a circle there. That's your radius. Now, how do we find our angle? Second tangent. So I got 75.96. Please, just like before, don't put 75.96 down. That angle would put you in quadrant 1, right? We need to be in quadrant 3. So what are we going to do? Add 180, so 255.96. And there is your answer. So again, I want you guys to think about this. The directions are different, the vocabulary is different, but the skill, the math, is exactly the same. You're finding the magnitude and the direction angle. That's all you're doing. Okay, now what about the other direction? What if you are given the polar coordinates and you need to change it into the rectangular coordinates? So let's change 2, 100 into rectangular coordinates. And please remember that alternative words for rectangular are Cartesian and complex. So rectangular, Cartesian, complex all mean x and y. Okay? So you've got this point 2, 100. So on my graph paper that I gave you, that would be like right in here. Would you agree with that? Now, you've done this before. It looks different, but you've done it before. I'm telling you, there's a little triangle here. And you know that is 2. And you know this is 100. So I'm going to draw it over here so it's a little bit bigger. You know this is 100, and you know this is 2. You're trying to find x and y. We just did that. Those are called the vector components, right? I've given you the magnitude and the direction angle. Now you're going to give me the x and the y, the components of that. So what did we do? Yes, that's how we did it. We used sine and cosine. So we can say cosine of, can't you really use 100, so we can say cosine 70 equals x over 2. So x equals 2 cosine 70. And then y is going to end up equaling 2 sine 70. But then if you do it this way, when you write down your ordered pair, you got to make sure x is negative.
Yes. Wouldn't it be 80?
Where'd you get 70?
Oh, I have no idea.
Okay, sorry.
Just totally made it up. Sorry about that. Hey, when you're my age, and you have as much chemo as I've had, and you don't feel well, you might make a mistake too. Probably not, but you might. All right, so cosine 80, x over 2. So I can get that answer has to end up being negative though. I gotta make it negative because why? Because x is negative in that quadrant, so it'd be 0.35. And this is 1.97. Now, yesterday, or whatever day that was that I saw you last, I told you that you could get a head start on your homework because one of the first things on there was some memorization. Did anybody do that? Anybody look at that memorization? No, why would we look at our pink sheet when it's not due for a couple weeks, right? Exactly. Okay, get your pink sheet out. Get your textbook out. Go to the page it says, calls them conversion formulas or conversion identities or something like that. Go to the page of your textbook. Oh, I said pink sheet, I think it's pink. Word 6-4 to 6-6. What's the very first thing it says? Memorize the coordinate conversions. All right, you find them? What does it say about X and Y? What does X equal? X equals R cosine theta. Y equals R sine theta. X equals R cosine theta. Y equals R sine theta. Now, here's the difference. If theta is in standard position, then you don't need to draw the picture and do all this stuff. Just type in, where am I? Just type in 2 cosine 100. Notice you get exactly the answer. You don't have to worry about changing the sign. And then we type in 2 sine 100, and we get exactly the answer. To change from polar to rectangular, it is so simple. Just use these. Now you're saying, well, Mrs. Ford, how come we didn't do that with the airplane? Because the airplane angles were not in standard position. This only works if the angle is in standard position. Remember, why weren't the airplane angles in standard position? Because they started up here. This does not work unless the angles are in standard position. Well, if you are given polar coordinates, that will automatically be in standard position. So if you want X and Y, X is 2 cosine 100, Y is 2 sine 100. That is so simple. So if you had to change,
Miss Ford,
what?
With the negative, is there a way that you would know without graphing that? Like 3, 5 would know? Isn't that negative?
Would be negative, you mean? Well, that angle is in quadrant 2.
Okay.
Yeah, I don't need to draw it to see it's in quadrant 2. It actually needs to be there. But you don't have to worry about that. Because with the conversion equations, you're typing in 100, it's going to come out negative. You don't have to change them if you use these equations. These equations can be used anytime the angle is in standard position. And the answers will just come out. So if our point was 3, 200, and your job was to find the X and the Y, X is going to be 3 cosine 200, and Y is going to be 3 sine 200. That's it. Type it in, that's your answer. You don't have to draw it, you don't have to find a reference angle, you don't have to change signs, you don't have to do anything but press buttons. Negative 2.82, and hopefully I'm pressing the right buttons. Negative 0.68. Now, does it make sense that they both just came out negative? Yeah, because where's 200? Third quadrant. So of course X and Y are going to come out negative. All right? So now we have changed from rectangular coordinates, that's X comma Y, into polar, and from R comma theta into rectangular coordinates. So now we're going to do the same thing, but we're going to do it with equations. Okay? So let's take a look at this equation. Let's say we have the equation X plus Y equals 3. That would be called a Cartesian equation. Now, why is it called Cartesian? Because its variables are X and Y. And that's what Cartesian means. Your variables are X and Y. So if we said, write this as a polar equation, then that would mean no X's and Y's, just R's and thetas. Right? Okay, now I just erased it, but I used it right here. What does X always equal r cosine theta. So I'm going to take this x right here, and I'm going to change it into r cosine theta, because that's what x is. And guess what I'm going to do with that y right there? R sine theta. So I took out the x, plugged in r cosine theta, took out the y, plugged in r sine theta. Now look at the equation I have now. What are the variables in that equation? R and theta. Would it qualify then as a polar equation? Yeah. Could you do things to it like factor out an r and stuff like that? Sure you could. But you don't have to. This is it. How hard is that? It's not. That's easy. All right, how about this one? X equals 2. That's a rectangular equation. What would it be as a polar equation? R cosine theta equals 2. Remember, from the beginning, x goes with cosine. From the beginning, x is cosine, y is sine. Okay, that was another extremely challenging problem. All right, how about this one? Now that's a rectangular equation. It happens actually to be a circle.
So it would be r cosine squared.
So, yeah, so it would be r cosine theta squared plus r cosine theta, or r sine theta squared equals 49. Now, we do have a little bit of work to do with this one.
You want to reduce it?
Because, well, I can square everything. So I have r squared cosine squared. I have r squared sine squared equal to 49. If I just square, you know, the things inside the parentheses.
Could you square root it?
No, I don't want to square root it, but I am going to do something to it. I am going to, I'm going to square root it, but not at this point. I'm going to square root it in a minute. I'm going to take out my r squared. What is so special? Now over here, I could have factored out the r for sure. And this is what I would have had. And I kind of discouraged you from doing
this
that.
is like one of our identities.
Oh my gosh, this isn't like one of our identities.
Which is one.
This is the fundamental trigonometric identity. Sine squared plus cosine squared is 1. So the equation really says r squared equals 49, which means r equals 7. Which is makes perfectly good sense, because this is the equation of a circle centered at the origin with a radius of 7. So what is this equation saying? Give me every point that's 7 units away from the pole. Well, every point 7 units away from the pole is going to be that circle, isn't it? Yes, indeed. I love it when it all comes together, don't you? All right, let's go the other direction. Let's suppose we have a polar equation, like, let's say r cosine theta equals 6. Well, if you're paying attention, this should pop right out at you. That's x. So this equation just says x equals 6. What about something different like this? Now, that's a polar equation. Why is this a polar equation? Because his only variables are either r's or thetas. or both, r's and thetas. And that's all the variables you have in here. You have one big variable and it's a theta. This is a hard one. What do you think?
Change to the sign of
All right, one option would be to change tangent into sine over cosine. What's another option? Tangent is y over x. Now, Jack, are you looking at your little green conversion box? Yeah. Now, we already know tangent is y over x, or I should say you're supposed to know that, but that is a conversion equation. Take a look at this, guys. Doesn't this say y equals 7x? Is that a Cartesian equation? It sure is. Its variables are x and y only. So you've got a toolkit full of stuff. If you get stuck in this little unit, it would be good to go to that green box, those conversion equations that I've asked you to memorize. But a lot of that you already have a good feeling for, just maybe in a different sense. All right, let me find one more. How about this one? Now, wait a second. Just stop, catch your breath. I'm giving you a lot of information. This is an equation. What kind of equation is it? Would you say it's polar, or would you say it is rectangular or Cartesian? It is a polar equation. So let's change it into rectangular equation. Now this is a little harder. So I'll give you a suggestion. Oh, go ahead, Dylan.
Would it be maybe negative x equals 4? Or no?
No. I don't think so.
Can you start by dividing by 4? -4?
You could. I probably wouldn't. Let me give you a hint here.
When you change cosine into
That's
x over
what I would
r.
do. You know what we did here? We took the tangent and we changed it into what we knew it was in terms of Cartesian letters. So let's do that, maybe kind of make a habit of that. If we're changing from polar to rectangular, let's at least think about changing the function, sine, cosine, tangent, whatever it happens to be. So what is cosine? X over r. So let's do that. Now I'm going to multiply by r to prove a fraction. Is that okay? Now, Jack, you're supposed to be looking at your green conversion box because something's supposed to be sticking out at you here. But I'm going to draw the picture. Here's the picture. This is x, this is y, this is r, and this is theta, right? Now tell me about r squared. Look at that picture. R squared is x squared plus y squared. It is the Pythagorean theorem. You use it all the time to find the magnitude. That's all we're doing, is saying r squared is x squared plus y squared. That's another one of your conversion equations in the green box. And now you have a a rectangular equation.
You just leave it like that?
Yes. Now, this is a circle. You could put it in standard circle form, but you don't need to. Your job was to make it Cartesian, and that's good enough. Okay? All right, well, we're going to go to lunch last, so you got to hang on a bit longer. And quit whining. You'll enjoy not having to come back. You only have to dread it once today. Get your calculators out. We're going to do a little graphing. All right, we got our calculators out. Okay, go to mode. We're going to shake things up a little bit.
Are you gonna go to polar?
We're going to go to polar now. Remember, you were in parametric. Now you're going over to polar. Let's go ahead and leave our calculators in degrees, or put them in degrees if they're not already there. Let's go to window. Now it says theta min. Now you left your calculator in degrees, so what do you think theta min should be? 0. Theta max should be 360. Now think about that theta step. We talked about it. 30 is probably too big, but 5 is probably okay. 1 would be great, but it's going to take a while to graph. So let's just start with 5. And let's leave our window at -10 to 10 for all of the things. Okay? Now, I'm just going to pull an equation out of the book here. And we're going to graph it. Okay? So we're going to graph this equation. So go to y equals, whoa. It's not y equals anymore. Now it is r equals, because you changed it to polar. So 4 cosine 3 theta. Theta is your x variable. It's your variable button. If you're in function mode, it's x. If you're in parametric, it's t. If you're in polar, it's theta.
All right. It's the X button.
Press graph.
Button. It's the same as the X, so it's the same as the X.
Okay. Now. Yeah, everybody listen. Okay. I'm not real excited about the picture I see, so I'm going to make 2 changes so I can maybe see it a little bit better. I'm going to go back to my window, and I'm going to make my mins and maxes for x and y 5. So my x's and y, min and max, are going to be 5 and -5. Okay, so my x min, y min, -5, x max, y max, 5. Then, okay, now when I graph, it's a little bit bigger picture. But now I'm going to zoom square. I'm going to zoom square. So I get a really good picture. Now, I want to talk one more time about why zoom squaring is important. Remember, the calculator screen is rectangular. So it is automatically going to pull things this way more than this way, because it has more room this way. So if you want to know what it really looks like, you got to zoom square. Now that's true no matter what mode you're in. Whether you're in function mode, parametric mode, polar mode, makes no difference. You want to zoom square if you want a good picture. Okay? This thing has a name. This curve has a name. This is called a 3-leaved rose. Now, I don't think there's any question about why it's 3 leaves. Right? I mean, obviously there's 2 leaves on here. And it's called a rose. All right, I wanted you to go back to your equation, and I want you to change one thing. I want you to type 4 sine 3 theta.
Along with the cosine.
No. New equation. So, before you erase, maybe take a look at what this one looks like. Did you remember what this one looks like? Because we're going to do a comparison. All right, so get a good visual of that, or maybe jot it down on your paper. And now we're going to graph 4 sine 3 theta. Did you get another 3-leaved rose?
Yeah.
You did, but you didn't get the same rose. What happened? It rotated. And Jack, we are not surprised by that, because this is a cosine curve, or sine curve. I mean, that's a sine curve, and this is a cosine curve. Aren't those exactly the same curve, except shifted? So in a Cartesian setup, we just shift them sideways. But in a polar situation, there's no shifting sideways, there is shifting around the circle. So they're just rotations of each other. All right. So the only difference between cosine and sine is going to be positioning. All right. So now, let me have you graph this one. If you are seeing jagged edges, you need to bump more points, which means you need to change your step. You should not be seeing a star. You should be seeing smooth edges. But if you need to change your step to something smaller, nice smooth edges, and it's kind of small, right? So wait a minute. What happened? Going from these guys to this one, what happened? What? Okay, the two in front, and what impact do you think that two in front had? Made it smaller. Whoa, stop. Back to this guy. When we graphed 4 sine x, that curve went up and down 4. But when we did 2 sine x, what happened? So, this is the same thing, only instead of the amplitude number being like up and down, it's how far out you're going. So these leaves went out 4 units. These leaves are only going out 2 units. So it's a lot smaller. What else changed?
How many leaves?
Oh, now you got 5 of them, right? Why do you think there's 5 of them? Because we put a 5 theta in there, right? So without graphing, tell me what this is going to look like. Without graphing, tell me what it's going to look like. It's going to be a 5-leaf rows. The leaves are going to be 2 units long, and it's just going to be rotated somehow, right? From the one that you graphed. Now you are all thinking that you've got this. Now I'm going to mess you up. Because now I'm going to have you graph this. And when you're done with that one, I want you to graph this one. And when, no, not together, graph them individually. And then when you're done, I want you to graph this one. Now remember, if you're getting any jagged edges, you need to change your step to a smaller number. It is possible that some of these will give you jagged edges with the setup that we have in place. Now, keep track of what's happening. I just graphed the first one, this one right here. How many leaves are there? 4. Whoa, wait a minute, 4. You told me over here, these were 3-leaved roses because of the 3s. And this guy, these were 5-leaved roses because of the 5. Well, now I've got a 4-leaved rose, and the leaves are 5 units long. I'll say inches, right? Okay, all right, just make a note, move on. What's this one? Leaves are a little shorter. They're only 3 units long. The land of Goshen, how many of them are there? This is an 8-leaf rose. They're 3 units long, but there's 8 of them. All right, let's try one more. Anybody have a spirograph when you were little? Oh, you don't even know you had a spirograph?
Like this,
No, that's a slinky.
no, not a slinky, but like it just like expands.
No.
Don't they create like perfect like circles?
Yeah, well, yeah, they make shapes like this.
Oh, yeah.
You have the little wheels that go around inside.
Yeah.
Yeah. Good. Every child should have a spirograph. Okay. Well, what happened here? What happened here? We got a 12-leaf rose. All right, I'm going to have you do one more, and then you're going to have to tell me what's going on. These leaves are 4 units long. Okay? Because there's going to come a day in your very near future when I'm going to give you an equation like this without a calculator. You're going to tell me about it. So let's do one more. Let's do R equals 5 sine 7 theta. Okay, so we're graphing 5 sine 7 theta. The leaves are 5 long. How many are there?
7.
Okay, so this gives me a 7-leaf rose. All right, and they're 5 units long. All right, so somebody tell me what in the heck seems to be going on.
I'm guessing it has to do with the number in front of the cosine and the sine being wrong.
Oh, yes, it does. Cassie, he said it has something to do with being even and odd. Do you want to maybe specify that for us?
Even to double it and then
So, if you're walking down the hall without your graphing calculator and you find this equation, you will be able to impress your friends and say, hey, look, it's a 20 leaved rose and the roses are 10 units long.
it's the number in front of
The number out here is the amplitude, just like it was before, but instead of being height now, the height of the waves, it's how long the petals are.
But then what's the number that decides?
This one right here.
So if that one's even, then it's double?
Yep. Yep, look, isn't that what happened? Look, when we had a 4 here, there were 8. We had a 6 here, there were 12.
Oh, 10.
Okay? There are 4 curves that are, okay, with polar coordinates, you can graph amazing things. So if you're kind of bored sometime, like in one of your other classes, I'm kidding. Get your calculator out and just type in some equations and start graphing. You can graph amazing things. Of all the amazing things you can graph, there are 4 families of curves that are called the classical curves. And one of them is the rose. So we have talked about the rose ad nauseum, okay? We get it, Mrs. Ford. A rose is going to have an equation like R equals A cosine B theta or A sine B theta, right? That's what a rose is going to look like. And what does the A tell me? How long the leaves are, how long the petals are. And the B tells me how many there'll be. If B is odd, there's B of them. If B is even, there are 2B of them, right? That's a rose. Okay, so now I'm going to have you graph the next classical curve. And no, Michael, you keep watching the clock. We're not going to do all 4 of them today. R equals 2 plus 3 cosine theta. All right, now stop. Does this equation look like a rose equation? No. Okay, you got to keep these things straight. Roses look like this. All right, So what does this look like? Let's type it in and see. Huh.
Oh, so apple.
Okay, it looks like an apple. Can anybody think of anything else it looks like if you were going to describe it? He said apple, a heart, and we're going to talk about that.
Not like a heart either. It's a peach.
A peach.
A peach.
Yes.
Think of a vegetable. Does it look like any vegetables you know?
Oh,
Who
tomato.
eats vegetables?
All right, we're not going to get into that conversation. Okay. This shape is called a lima sign. A lima sign. A lima bean. A lima bean. It looks like a lima bean. Okay.
A lima bean.
A lima sign. It's pronounced lima sign. Okay. And a lima sign is this shape. Now, this particular lima sign has what we call an interior loop. They don't all have that. So let's go back and let's type 2 plus 2 cosine theta. Now, that's still a lima sign, but it doesn't have the little loop inside of it. Because these two numbers match, it's still a lima sign, but it's a special lima sign called a cardioid because it looks like a heart. So lima signs are this big group of like dented in circles, peach shapes, lima bean shapes. If these two numbers have the same absolute value, so for example, it could be 2 minus, okay? If these two numbers have the same absolute value, then you're going to have a special lima sign called a cardioid. Okay? Oh yeah, sine or cosine. Yep, let's do a sine. Lima sign. We're talking about lima signs right now. So think of it like this. You know how in geometry you got rectangles? But if the length and the width match, you have a special rectangle called a square. That's what's happening here. We got lima signs. If these two numbers happen to have the same absolute value, then you have a cardioid. All right, let's graph one more of these. Let's graph, because we haven't done a sign yet, so let's do a sign. Let's do 4, I gotta be careful, 4 minus 5 sine. Uh-oh, what happened?
What is that?
Mine went off the screen. Did yours? Okay. Why is it flat? It should be flat. Yeah. Well, this is a big one. I want you to think about something for a minute. Sine and cosine, but for this problem, sine goes between -1 and 1. So if sine happens to be -1, this is going to go all the way to 9. So that's why it's off the screen. So I may want to make that adjustment if I think about it. If not, you can do it afterwards so that you can see the whole picture. The interior loop is a little bit squished, as Jack may have pointed out, but there is an interior loop there. Did you watch it as it was graphing? This is not a cardioid. Why is it not a cardioid? Because these two numbers don't match. Right? Now, what does the equation of a Lima sign look like? It's got a plus in it. It's going to be the only one of our equations that has a plus or a minus. So it's going to be A plus B sine theta, or A minus B sine theta. And these could also be cosines. These could also be cosines. So maybe I'll do it this way. A plus or minus, A plus or minus. I'll make this. If A and B happen to have the same absolute value, then you have this subgroup called a cardioid. So we got two more families to consider, two more families of the cosical curves. Right now, we talked about the rose and the Lima sign. You can tell those equations apart because the Lima sign equation is always going to have a plus or a minus. The rose equation is never going to have a plus or a minus. It's a multiplication. Okay? All right, let me check my time. Oh, I don't think so. No, I don't think so. All right, so now we're going to go on. Come on. If you're going to have one big long chunk of math, this is good stuff to be talking about. This is fun stuff. So now we're going to try this equation. R squared, oh my, that's different. R squared equals 16 sine 2 theta. How do you graph that? Great question. Because when you go to graph, it doesn't say R squared equals, it says R equals. So guess what we're going to do? We're going to take the square root. But boys and girls, you need to do plus or minus. So you're going to type in two equations. And I'll be real honest with you. Sometimes it matters if you type in both of them, and sometimes it doesn't. We never know. So just get in the habit of typing in both of them. At the same time, pressing graph, and tell me what you've got. It will not be a rose, and it will not be a Lima sign. It is something different. You got a figure 8. I love it. A figure 8 is what we call a lemniscate. A lemniscate. But sometimes, this isn't the way you say it, but it might help you remember. Figure 8 lemniscate. Wrong pronunciation, but it goes with the spelling and it may help you remember it. Figure 8 lemniscate. Okay, it's actually called a lemniscate, but it's spelled lemniscate. So figure 8 lemniscate. What was different about this equation? The squared. This part of it looks like a rose, right? But this makes it a lemniscate. All right, let's change the sign to a cosine. What happens if you change the sign to a cosine? Anyone want to take a guess before you do it? Just going to rotate. So which way did your figure 8 go originally? First and third? All right, let's see what happens when you make it a cosine. What is it? What happened? So now it's in, it wasn't in 2 and 4, was it?
It was in 1 and 3, and now it's in all 4.
Now it's in all 4.
Yeah.
It's an infinity sign.
Oh, I see what you're saying. It's on an axis now. Yeah, so it's like this. Yeah, so it's horizontal. Instead of being diagonal, it is horizontal. Yes. So you got the exact same figure 8. It just rotated exactly like you expected it to. Okay? So the equation of the lemniscate, R squared equals something times sine 2 theta, or something times cosine 2 theta. with a lemniscate, that will always be a 2 theta. If you graph, it is currently possible to make it another theta, but it won't be a lemniscate then. It will be some other shape, which is fine. All right, so we'll know the equation of a lemmason because it's going to have a plus or minus in it every time, and add or subtract. We'll know a lemniscate every time because it's going to have an r squared. And now we're going to talk about the last curve. Jack?
Mine has like a depth.
Yeah, that's okay. Some kind of setting that you have in there, you have to change it to make those points show up. I don't know exactly how to do it. It's fine. It's okay. The gap is connected. Jack is connected. Okay? The calculators aren't perfect, and sometimes they don't quite show everything. All right. So now I need everybody paying attention, because now we're going to make some major changes to the calculator. Okay? Okay, we're going to go to our mode, and we're going to go into radians, and we'll talk about why in a minute. And we're going to go to radians. So we're going to mode, last classical curve. We're ready to do it right now. When we're done with it, we'll go to lunch, okay? No, lunch hasn't started. Lunch ends at 12:55. No, you don't get a 50-minute lunch or a 40-minute lunch. Okay, so we're on radians. Everybody on radians? All right, now I want you to go to your window. And since I am now in radians, if I were doing any of the rest of these, I would go from 0 to 2 pi. But I'm going to ask you to go from 0 to 20 pi. So 20 pi.
That's a lot of pi.
It's a lot of pi. Now, as soon as you press enter, it's going to go to a decimal, and that's fine. But we're going from 0 to 20 pi. Now, for theta step, we are in radians. So we need to do about 0.1. We're going to try 0.1, because we're in radians, which is a smaller unit. X min, negative 150, positive 150, and the same for y's. Negative 150, positive 150.
You need a scale of 30.
I have a scale of 1. I don't care what your scale is. It doesn't really matter. All right. Now I want you to type in the equation R equals 2 theta. There is no function, no sine or cosine or anything in that, just simply 2 theta.
Why is it not stop?
It says error.
I keep going.
That's crazy.
What do we got?
Spiral.
You have a spiral. The fourth classical curve is the spiral. Now, you will recognize the equation of a spiral because all the rest of them have a sine or a cosine in them, and this one doesn't. So what I'm trying to do is help you keep all these equations straight. You will know the equation of a lemniscate because it's the only one that has a square. You will know the equation of a lemmason because it's the only one that has an add or a subtract. You will know the equation of a spiral because it's the only one that doesn't have a sine or a cosine in it. Right? Easy. Now, the spiral that you drew, somebody said, well, why isn't it stopping? Well, it did eventually stop. But if you counted, it went around 10 times. Now, I planned that. When I told you to go up to 20 pi, 20 pi is 10 revolutions, because every revolution is 2 pi. So I wanted this to spin 10 times, just so you could see a nice spiral. If I'd gone from 0 to 2 pi, which was what I would normally do, you wouldn't have seen a spiral. It would have gone around one time and stopped. If you're going to spiral, you obviously have to tell it to go around more times. Now, why did I not want to do this in degrees? Because 10 revolutions in degrees is a huge number. 3,600, but I'm doubling it, so my window would have had to have been like 7,500 by 7,500. Since I use radians, and I'm only going 62, then I could get by with 150. 2 162s is 100 point something. So that's one. Does that make sense to you? Okay. Right now, you should be able to get a good start, maybe even do all of, I can't remember everything that's in 6-1, or 6-4, I mean, but you should be working on 6-4, getting started on that. This is another quick unit, because there's only 3 sections, right? So it won't be long, and you'll be having another test over this.
No way.